All right, recap. So we've been talking about density-dependent, density-independent factors, populations, community. Out of population, community, and ecosystem, which one has living and non-living things? Ecosystem. Which one is just all the living things? Community. Which one is the living things that are of the same species? Population. Okay, good. We talked about density, right? So density is how clumped they are, right? How many individuals are in a specific area. So if I wanted to find density, if I had like 10,000 deer in 500 acres, what could I do to find the density? Divide by the area, right? So the number divided by the area, right? So if I had 10,000 deer in 500 acres, I'd just take 10,000 divided by 500, right? So I could find the density. And what the density is telling us is, are there a lot of deer in per area, or are there a little deer per area? And different areas might have different sizes, so we want to know, how do the deer compare per area? Okay, so we talked about factors that affect the population, limiting factors. They can either depend on density, density-dependent factors, or they can be independent of density, so density-independent factors. What are some density-dependent factors? Food, what else? Space, what else? What did you say? Disease, water, habitat, predation. Okay, what would be some independent factors? Okay, human causes or weather. Okay, so density dependent, density independent. What we're going to be talking about today is we're going to talk about populations and population growth. Okay, so with populations and population growth, there are some math. There's some math in this unit and in next unit. The math problems are not complicated. The formulas are not complicated. There are a couple of formulas you need to know for the AP exam. One of them is as easy as you take 70 divided by a number. That's the formula. Okay, so they're not hard. Okay, promise you it is nothing like the beginning of the school year. Okay, so here's an example. This example is on your sheet. So it says if the population growth rate is 0.5 per year and I start out with 500 individuals, how many will I have after 1 year? Anyone have any guesses what we should do? The 0.5 means there's 0.5 individuals added per year. Okay, 0.5 individuals. For every one individual, there's 0.5 added each year. So if I start with 500, what could I do to figure out how many are going to be added? Multiply by 0.5, right? So if I take 500 individuals and I multiply by 0.5, that's going to tell me how many individuals are added, right, to the population, because I'm going to end up with 250. Now, 250 is not my total population, right, because I started with 500. So what's my total population going to be? 750, right? So just 500 plus 250 equals 750. So that's my population after 1 year. Now, in order to find it after the next year, all we have to do, 750. Again, we multiply it by 0.5, the growth rate, right? This means for each individual here, half, 0.5 of an individual is going to be added. Okay, so we'll get 375. Again, 375 is not my population. In order to find my population, I just have to take 750 plus 375. Okay, I end up getting, I think it's 1125. We'll go with that. 1125. Okay. So these are the types of problems that you might see. They have some of these on old AP exams that I've looked at, okay? So that's why I'm having you do them. This is literally the most math that they typically have you do, is all in the population unit, and it's not anything super complicated, but people typically forget because it's like, I don't know, they're studying everything else, and they only learn it one time a year, and so they end up forgetting. So it says in this one, growth rate, right? So the growth rate is equal to, and of course, you know, it didn't have a spot where you could write this. But the growth rate here is the same equation that you already know, right? Do you remember the percent increase or decrease? It's the same thing as the growth rate. The only difference is you just don't multiply by 100, okay? So you just take the difference, divide it by the original, and you don't multiply by 100. The reason we don't multiply by 100 is because we're not saying what's the percent increase, we're saying what's the growth rate, okay? So like in our past example here, we're not saying the growth rate is 50%, we're saying it's 0.5 individuals per year. So that's why we don't multiply by 100, okay? So for example here, if the starting population is 50, ending is 55, what's the growth rate? So we would take 55 minus 50, which would be 5, and we take it over the original. So 5 divided by 50. So what's going to be my growth rate? 0.1. Okay. So those are the two types of problems that you're going to kind of have to know at least right now. Okay, there's another formula when we get to human population, which is our next chapter, so we'll talk about that next week. But I have some practice problems, and in the interest of time, oh, that's definitely not the right worksheet. I will do these with you. Press them back. All right, see if you can do number 1. I'm going to pull these up here. All right. So if I start with a population of 5,000 dolphins, after 5 years, population is 5,500, what's the growth rate? So we know the growth rate is just the difference divided by the original. So what's my difference going to be? 500, okay. And what's my original? 5,000, right? So my growth rate is going to be 0.1. Now this is for the entire 5 years. If they were to ask you what's the growth rate per year, what would you need to do? This is for 5 years total. Divide by 5, right? If they asked you per year, okay? If they just ask you what's the growth rate over this period, you could just say 0.1, okay? Number 2, starting population is 10. What's the difference? 30 divided by the original, which is 10. Okay, so we're going to end up with 3. So what this is telling us is that for each individual in the population, we are adding 3 individuals, right? And that makes sense because we start with 10, we end up with 40, okay? 3, if I start with a population of 200, after I end up with 250, what's the growth rate? So the difference here is 50, so 250 minus 200, so 50 over the initial, which is 200. So 0.25, and again, that's for the whole 10 years. If I wanted per year, what would I have to divide by? 10. If the population of monarch butterflies is 2,000 and the growth rate is 0.2 per year, how many individuals will there be after 1 year? What do I need to do here? Yeah, 2,000 times 0.2. So if you do 2,000 times 0.2, what do you end up getting? Times 0.1 is going to be 200, so we're going to end up getting 400. Okay? So 400, what's my answer though? 2,400, right? Because I have to add that 400 to the initial population. So my answer then would be 2,400. Okay, number 5, scroll down here. If the population of wolves is 10 and the growth rate is 0.1 per year, how many individuals will there be after 1 year? So I'm going to take what times what? 10 times 0.1? So I end up getting, when I take 10 times 0.1, I end up getting 1, right? So how many wolves are there going to be after a year? 11, right? Because we had 1 to the 10. Okay. Now, in order to do it after 2 years, we're going to have to take 11 times 0.1, which is going to be 1.1. So basically, we're adding another wolf. Right? So after 2 years, there would just be 12. All right, lastly, population of tortoises starts off at 15,000. Growth rate is 0.3 per year. So I'm going to take 15,000 times 0.3. We end up getting 4,500, so 4,500. So what's my final answer going to be? What's the population? 19,500. All right, you can keep this sheet to look back at. We need your note packet. So a lot of times when we talk about populations, we'll see that they have specific cycles, okay, or specific patterns that they show when they grow. So we're talking about how do populations grow, why do they grow, all of that stuff. Some of this should be review from bio, okay, or if you're in AP Bio, it'll be review, or I don't know if you learned it yet this year, but. So how do we model population growth? We've got lots of different graphs. So the first one's exponential growth. Exponential growth shows a J-shaped curve, and it shows a population growing at what we call its biotic potential. The biotic potential means the maximum growth we see So in that little square next to exponential growth, just draw a J-shaped curve like that. Everyone good? Okay. So typically what we end up seeing is they don't experience this exponential growth forever, and they end up leveling off, right? So we have what's called the logistic growth model, this S-shaped curve that they typically end up showing. Our limiting factors are more at play. Fast. All right, R. So if you just want to write high intrinsic growth rate, if you want to write that they experience offshoot and die off, you can, kind of up to you. So because they grow so fast, a lot of times they'll overshoot their carrying capacity. And then what we end up seeing is they end up dying off. So they have a lot more unpredictable population growth. So the opposite characteristics here, short lifespan, many offspring. All right, so now you have some time if you want to work on the R and K thing that you did not get done.